This is RM4D, a combined reachability and inverse reachability map for common 6 and 7-axis robot arms by dimensionality reduction to 4D. Using RM4D as forward map, we can predict whether a certain pose is reachable by the robot. Using RM4D as inverse reachability map, we can suggest where the robot space should be given a target tool center point position or pose. Existing approaches build a reachability map by discretizing the robot's 6-dimensional workspace. First, they voxelize the 3D space, and then they discretize the orientation based on the approach direction and the in-plane rotation. The inverse map is then a separate data structure of the same type and must be built from the forward map. Instead, our RM4D uses the same data structure as both forward and inverse map. We further achieve a dimensionality reduction from 6D to 4D, which reduces the memory requirements and the construction time of the map by an order of magnitude. Yet, we reach state-of-the-art accuracy. So in short, we can do what two 6D maps can do with one 4D map. Let's see how this works. We make two key assumptions. First, we assume that the wrist joint can do a full rotation, which allows us to ignore the in-plane rotation. Second, we assume that the base joint can do a full rotation as well. These assumptions hold true for many common 6 and 7-axis robots, but not for all, including the Franka Panda that we see in this animation. Let us stick with the assumptions for now, and we will explore this further. As shown in the animation, we employ a canonical transformation to achieve the dimensionality reduction. We then store the z-value of the TCP, the angle between the approach vector and the z-axis, as well as the canonical base position in our map. This gives us the 4D structure. We can query it as forward map using the same transformation, and we can query it as inverse map by directly retrieving the canonical base positions for a given TCP pose. Looking at the results, we see the accuracy, the true positive rate or recall, and the false positive rate over the number of samples required to build the map. We notice that RM4D requires much fewer samples to get to an accuracy above 95%, which means that it can be built much quicker. Since we made assumptions, we would expect the false positive rate to be higher, but this is not necessarily the case, even for the Franka Panda in the top half of the plot. Investigating this further, we artificially changed the joint range to make the Franka violate our assumptions more gradually. We can see that the accuracy remains high even when the joint range is reduced to plus minus 150 degrees. RM4D can be applied, for example, to grasp planning scenarios for a mobile manipulator. Given these 4 objects, RM4D suggests a suitable base position from which all of the objects can be grasped. Thank you for your attention, and feel free to visit our project page or get in touch.